Hi, chemistry. We're going to talk a little bit more about ions today because we are getting into ionic bonds. So compounds that have ionic bonds are made out of ions. Compounds that have ionic bonds, when you recognize the formula, you're going to look for something that has a metal plus a non-metal. And the reason that metals and nonmetals tend to react together to form ionic bonds is because they have such a large difference in electronegativity. The metals have a very low electronegativity. Nonmetals have a very high electronegativity, and that electronegativity is the attraction of the atom, or the ability of the atom to attract, right? To attract what? To attract an electron. And so basically, because metals have such a low attraction for the electron, they allow the electron to leave and go to this element, this nonmetal that has a very high electronegativity, has a very high attraction for the electron. So the electron is going to leave the metal and be attracted to the nonmetal. That leaves the metal as a cation because it has lost electrons. That leaves a nonmetal as an anion because it has gained electrons. So really what we're talking about when we're talking about an ionic compound is or a compound that has an ionic bond, we get this giant lattice that's made out of cations and anions. And because one is positive and one is negative, they're going to have this really strong attraction for each other, and it forms a very strong bond. That's what an ionic compound is. So in order to understand ionic compounds, we really need to understand the ions inside of them. We need to know what their charges are so that we can figure out how many of each come together to form a stable compound. And we need to understand what the ion names are so that we can understand how to name an ionic compound. When you name an ionic compound, basically what you're going to name, you're going to give the cation name plus the anion name, and those two things together equal the name of the ionic compound. So it's a pretty simple system as long as you know how to name ions. So that's what we're going to talk about today. We've talked about a couple ions that come from a couple of regions in the periodic table, and then we're going to add to that today so that you are very prepared with cation and anion names, and then you can put those together into an ionic compound name. So let's begin by talking about what we already know, right? We have already talked through ion names for some ions, right? We've talked about ion names for representative cations and representative anions. So we talked about how on the metal side of the periodic table, which is basically this little section, that was an interesting line. It does technically involve this section as well down here. These are the inner transition metals, but the inner transition metals are so radioactive that they really don't form chemical changes. They don't form compounds. They don't undergo chemical changes to form compounds. They really are involved more so with nuclear changes. But we can include them if you want to. Okay, so these are all the metals, but there's really only a very few that are actually representative metals. The representative metals are going to be the first two columns, so the S block, and then any metals that are in that last 6 columns, so that's the P block. So S block and P block metals are going to be our representative cations. And remember, when we're talking about what ion forms from these, we really have to look at the valence electrons, and then we have to decide, are they going to gain or lose electrons to be full or empty, to have full or empty valence shells, right? And then the number that the metals are going to lose is going to equal their charge. So for example, if we pull off magnesium, which is buried underneath my coloring. Okay, so there we go. There's magnesium. If you look at magnesium, magnesium has 2 valence electrons, right? So magnesium is going to lose 2 electrons to have that empty valence shell, and therefore magnesium is going to have a 2+ charge. Now the same is true for things down here, like if we look at lead, for example. Lead is in the carbon family. The carbon family is going to have 4 valence electrons. So lead is going to lose 4 electrons, and it will have a 4+ charge. So you know how to determine what ion forms for the representative cations, for the representative metals, those S and P block metals. We've also talked about how to name the representative cations. So when you name a representative cation, all you do is you put the cation, the element name, plus the word ion. So for this Mg2+ ion we talked about, that would be the magnesium ion. We just took the element name and added the word ion. Now lead is a little bit different, and we'll talk about lead in just a minute when we talk about the transition ions. But for any of these S block metals, this is true. You just take the element and tack on the word ion. So that is true for S block metals. Okay, why don't you give this a go? Tell me what ion is formed with potassium, and what is its name gonna be? So ion charge and ion name. Go ahead and predict that. All right, now let's talk about the representative anions. So anions are formed by, excuse me, by nonmetals. So that's going to be this section of the periodic table. And the representative nonmetals are those, that's our P block, right? Plus hydrogen. Don't forget about hydrogen. Hydrogen is a nonmetal. Again, when we talk about the ion, these are going to have the exact same process. So you're going to have to determine the valence electrons. You want to determine all the nonmetals are going to gain electrons in order to be full, have full valence shells. And the number of electrons that they gain will be equal to their charge. So if we look at like oxygen, for example, oxygen has 6 valence electrons. It's going to gain 2 to have a full octet, and therefore it will be a 2-. Remember, it's going to gain 2 negative electrons. If it gains negative things, it becomes negative. And then we talked about naming these as well. You take the element name, take the ending off, and add the suffix "ide" plus the word ion. So oxygen, O2-, would form the oxide. I started to write oxygen. Let me write that over again. The oxide ion. There we go. Iodine would form a similar pattern, right? So iodine has 7 valence electrons. It's going to gain 1 electron in order to have that full valence shell, that full octet. So it will be a 1- ion, and its name will, instead of being iodine, it will be iodide ion. Okay, so you try phosphorus. Go ahead. Tell me the charge that phosphorus forms and what its name, the name of that ion will be. Okay, so now we get to the transition cations. So these mostly come from the transition metals. Now the transition metals are here in the D block. However, they're going to form patterns of ion forming and naming that are different than the representatives. And they actually are going to include some metals down here as well. And we'll talk about why some of the P block metals get included in this pattern. Okay, so for now, let's focus on the transition cations. So here's what's special about the transition cations. They contain a D shell. If we look at just the first one, scandium, for example, look at calcium, a representative metal, right? The electron configuration is this, versus scandium, a transition metal with the electron configuration. Oops, we can't forget the 4s there, can we? Okay, 4s2, 3d1. Notice scandium has an open D shell. Scandium already has an electron in the D shell. Any electron transitions that it goes through can now involve the D shell. And so because of this, scandium gets these really weird possibilities, which are the same for all transition metals. And so transition metals, because they have this D shell available to them, a lot of them can form more than one charge. Like copper, for example. Copper can form copper 1 or copper 2. Now, why do they do this? They do this because of that open D shell. The D shell kind of gives them more opportunities. Is there a nice little pattern as to which ions they form? There really isn't. Copper, for the example we gave, copper is here. Copper forms a 1 plus and a 2 plus. Well, silver, just below it, silver doesn't. Silver just forms a 1 plus. If we look at iron, just a couple over to this side, iron actually forms iron 2 plus and iron 3 plus. So there are some patterns. The more you learn about atoms and orbitals and electronic structure and molecular structure, the more patterns you're going to see come out of this. But they're just too extensive for us to cover. And even after taking this full year and the next full year of chemistry, that first year of college level chemistry, you're still not going to have great reasons as to why some of these form the ions that they do. And so it leaves us with but one option, which is to memorize them. So transition ions, a lot of them can form more than one charge. And there's not a great pattern on the periodic table to help you figure out why. And this is the connection to some of these other P block metals. Some of these other P block metals can also form too, like lead that we talked about before. Lead can actually form a lot of different ions. It can form lead 2, lead 3, lead 4. There's even some obscure ones that lead can form. Tin as well can form tin 2 or tin 4. Whereas aluminum, on the other hand, aluminum forms Al3+, and that is it. Aluminum doesn't have a second ion that it can form. And so transition ions get tricky. You just have to know which ones they form and which ones they don't. So as we start out here and we start using some of these cations in ionic compounds, I'm going to give you a list. I'm going to attach it to the next couple of days on Google Classroom. And that list is what you're going to have to reference as we start working with ions inside of ionic compounds, so you know what charges they form and what their names are. So because they can form multiple ions, we can't just name them like we name representative cations. So for example, if we look at copper, let's go back to copper, right? We had copper 1 and copper 2 plus. Well, if we use the representative way of naming this, we would get the copper ion for the first one, and then the second one would be named the copper ion, right? They would be named the same thing. So because copper forms 2 ions, we need 2 different names for those ions. And so here's what we do. We put the charge as a Roman numeral. So the copper that has the 1 plus charge, we call it the copper 1 ion. The copper that has the 2 plus charge, we call it the copper 2 ion. So here's the rule for naming transition metal ions. If they form more than 1 charge, you must indicate the charge with the Roman numeral. Notice that is the charge of the ion. We're going to start using these ions, and there's going to be other numbers associated with these ions. So it's going to be really important that you remember that this Roman numeral represents the charge and nothing else. That's worth saying to yourself multiple times. Another point here is that if something forms only 1 ion, like silver, for example, silver only forms a 1 plus charge. So when we name this, we do not put a Roman numeral in there. So if it forms more than 1 charge, you must include a Roman numeral. If it does not form more than 1 charge, you must not include a Roman numeral. That takes some getting used to. It takes some practice in this. So as we practice with this, I'm going to be careful to check that for you. Please be careful to check that for yourself as well. So let me show you that chart of the transition metal ions that form. And then after we look at that one, we'll come back to this last category, and we'll talk about polyatomic ions. Okay, so here's our transition or D block elements. Notice that a lot of them come with Roman numerals, right? Some of them do not. So silver, cadmium, zinc, notice that their names do not come with a Roman numeral. And so that indicates they only form that 1 charge. They don't form a second charge. Also, notice this is our transition or D block elements, but it does include tin and lead. Notice that tin has a couple charges, so does lead, right? And tin and lead are over here in the P block. So because they form more than 1 charge, they get treated like transition elements, even though the atom is technically located in that P block. But again, they can form multiple charges because they now have access to a D block. It gives them crazy, crazy ideas. All right, so this is the table that you're going to have to really be careful to reference when you're naming some of these metal ions. Okay, last category are the polyatomics. Polyatomic ions are exactly what they're named. Poly means many, and then atomic means atoms. So they're many atomed ions. So look at all of these listed in this chart down here. All of these contain more than 1 atom. So like Cn minus, the cyanide ion, is going to be a carbon atom connected to a nitrogen atom. And because this whole complex has a charge, it's an ion. Some of them get a little bit more complicated, like look at sulfite. Okay, sulfite is a sulfur connected to 3 oxygens, and it also has an overall charge of a 2 minus. So because the whole complex is charged, it's an ion. It acts just like an ion. Now, a couple of things to notice from here are that most of our polyatomic ions are negative, right? A vast majority of them are negative. We actually only have 2 polyatomic ions that are positive. This is not an exhaustive list of all the polyatomic ions that exist. This is just a list of the polyatomic ions that we're going to use and reference in our chemistry class. Again, this is on that same sheet, the sheet that lists out the ions. And so as you start to use polyatomic ions, you're going to have to reference this sheet until you get familiar enough with these ions that you just have them memorized and you can use them without the sheet. Okay, so let's talk about naming. The charges are given to you in this table. How will you know the charge of them? Because they're given to you in this table. The names are a little trickier. So let me point out a couple things about the names here. First of all, notice that a lot of them have similar endings. There's a lot of 8s and a lot of ites. 8s and ites, 8s and ites. There's only a couple that end in ide. Most of them end in 8s and ites, and that's for a reason. Here's another ide, 8, ite, 8, 8, 8. Okay, so a lot of these negative polyatomic ions ends in 8s and ites. So what those are oxy anions. So anions means they have a negative charge. Oxygen means they involve oxygen. So they're anions, they're polyatomic anions that involve oxygen. And the 8s and the ites tell you something about them. So the 8 is actually, the 8 form of them is actually the most common form. So when you are detecting ions in the Earth's crust, in the Earth's atmosphere, anything like that, the most common form that you tend to run across is going to be named with the 8. Now that's really informative. Thank you for letting me know that. However, not super helpful when we're trying to remember the names, right? So a good method of going through and memorizing these ions is to memorize all the 8 forms, because those are the ones that you're going to come across the most. They're the most common, right? So they're going to be the most common in compounds. They're going to be the most common in reactions. They're the most common. Now the ite form actually has 1 less oxygen. So look at like sulfate and sulfite. Notice they both contain sulfur, they both contain oxygen, they both have the same charge, but sulfite has 1 less oxygen. It's SO3, 2 minus, whereas sulfate is SO4, 2 minus. We see it in nitrate and nitrite as well. Nitrate is NO3 minus. Nitrite is NO2 minus. So same atoms, nitrogen and oxygen, same charge, negative and negative, but nitrite has 1 less oxygen. Notice also if you compare the 8 forms, nitrate and sulfate, not much is similar between them other than the fact that they both contain oxygen, right? Nitrate is a 1 minus charge. Sulfate is a 2 minus charge. Nitrate has 3 oxygens. Sulfate has 4 oxygens. So like I said, that 8 form doesn't indicate much, except it's the most common form of the ion in that family. Now there are 2 more prefixes. One is a hypoite. Let's see if I have any of those listed on there. Oh yeah, hypochlorite is right here. A hypoite form would have 2 less oxygens than the 8 form. So chlorate, ClO3, chlorite, ClO2 minus, hypochlorite, ClO1 minus. And then the other form is the per8. The per8 form has has one additional oxygen than the 8 form. So you can see perchlorate here. If chlorate is ClO3 minus, perchlorate is ClO4 minus. Notice it has gained an oxygen. So that's one of the ways to approach to understand the naming within these polyatomic ions, is that the oxy ions really exist as families, and they are named relative to one another. So now you know the difference between 8 and 8. You know where the per and the hypo prefixes come from. It's all part of the name of these polyatomic ions. You can also see some of them end in "ide," like these 3 that I've circled: cyanide, hydroxide, peroxide, all end in "ide." And then the cations up here, they have different endings as well. Ammonium. So you don't see that ending down here at all. And then dimercury is completely different, right? The di is referencing how many mercuries are in there. And you don't see that in any of these other names. You don't see anything indicating the number of the atoms within there. That's the only one. I will point out this one, hydrogen phosphate. Notice hydrogen phosphate is just phosphate with a hydrogen attached. So here's the hydrogen phosphate compound. Here's the phosphate compound. So notice they've attached a hydrogen. Instead of PO4 3 minus, it's HPO4 2 minus. And because they've attached a hydrogen, which is a H plus charge, it's dropped the polyatomic charge. So PO4 3 minus took on an H plus and become HPO4 2 minus. That's what adding this hydrogen prefix means. Okay, so again, you're going to be really married to this chart for a long time until you are familiar with these names and you've kind of memorized enough of them to break free and operate without this chart. All right, so welcome to ions. Now that you're a little bit familiarized with these ions, now we can start using them in ionic compounds. So let me know what questions you have. I'll see you in class.